Good afternoon. This file contains the pre-lecture slides for class on Tuesday, September 3rd, 2013. The relevant reading for this lecture is from the 8th edition of our carry text, sections 2.1 through 2.10. This week we begin our study of organic chemistry in earnest with a look at our first organic structures, the hydrocarbons, which are compounds constituted entirely of hydrogen and carbon atoms. To best understand the structure and reactivity of organic compounds, we will introduce basic concepts of molecular orbital theory and valence bond theory. From this lecture, it is important that you learn how to distinguish between different types of hydrocarbons, such as alkanes, alkenes, and alkynes. Also, be sure that you understand how valence bond theory and molecular orbital theory explain the hybridization of atomic orbitals to explain the formation and stability of covalent bonds. Note that molecular orbital theory offers the most accurate description of bonding, structure, and reactivity and will be used throughout the semester. First off, who cares? Why am I learning this? Well, hydrocarbons comprise all fossil fuels used by the energy industry and most of the plastics that you encounter on a daily basis. Understanding the chemistry of hydrocarbons will help you better understand the trade-offs using fossil fuels on our lives and environment, as well as the benefits and health risks associated with different plastics. Chapter 2 is your first introduction to hydrocarbons, and as we move through the semester you will learn different processes for making hydrocarbons, as well as how to convert them into other substances. For those of you who don't get jazzed by fuels and plastics, consider that hydrocarbons are the simplest organic compounds we will deal with this semester, and a firm understanding of their structure, nomenclature, and reactivity will provide a strong foundation for later concepts in the course. Okay, so to begin, organic chemists classify all hydrocarbons into two different categories of compounds. Aromatic compounds contain aromatic structures like the benzene structure shown here, and all other compounds that follow Huckel's rule. Here at the start of the semester, we will focus primarily on aliphatic compounds and focus on aromatic compounds later on in the end of the semester. Aliphatic compounds can be further divided into alkanes, alkenes, and alkynes. Notably, all aliphatic compounds are those compounds that are not aromatic and contain only carbon and hydrogen atoms. At the bottom of the slide, you will see the generic formulas for alkanes, alkenes, and alkynes that can be used under most circumstances to determine which type of aliphatic compound you have if you only have the molecular formula on hand. First off, alkanes are hydrocarbons that contain all carbon and hydrogen atoms bonded together with single bonds. Notice the example structures on the right, which all contain single bonds. If you're still unclear about how to read the bond line diagrams introduced in week 1, take the time to draw out each C and H atom in the three structures you see here. The top structure has formula C5H12, the branch structure on the right has formula C6H14, and the ring structure has formula C6H12. See if you can find all the carbon and hydrogen atoms that are implied by these bond line diagrams. Alkenes are hydrocarbons that contain all C and H atoms with one or more double bonds. Notice again the example structures on the right, each of which contains at least one double bond. Once again, it's good practice to draw out the carbon and hydrogen atoms in these structures. For your reference, the top structure has formula C5H10, the branch structure on the right has formula C6H12, and the ring structure has formula C6H10. Finally, alkynes are hydrocarbons that contain all carbon and hydrogen atoms with one or more triple bonds in them. Notice the example structures on the bottom left, each containing one triple bond. Here, the structure on the left has formula C5H8, and the structure on the right has formula C2H2. Given we now know the names of some classes of basic organic compounds, we can begin to explore the differences in shape, geometry, and structure for each class. To do this, we will make use of valence bond theory and molecular orbital theory. Recall that the Lewis model of bonding did not account for the wave properties of electrons. These latter two theories attempt to reconcile the wave properties of electrons with the empirical data we have about molecular shape and geometry to better explain how covalent bonds form that give rise to each class of hydrocarbons we've discussed. Briefly, valence bond theory states that covalent bonds form from constructive interference between electron waves of two half-filled atomic orbitals. Molecular orbital theory advances this concept by deriving the unique wave functions for individual molecular orbitals in the same way that Schrödinger did to derive individual atomic orbitals. First, let's examine the valence bond theory. This theory states that electron pairs can be shared between two nuclei when a half-filled orbital of one atom overlaps in phase with the half-filled orbital of another atom. We can look at the formation of the simplest molecule, molecular hydrogen, to further explore valence bond theory. In molecular hydrogen, a covalent bond exists between two atoms of hydrogen. Alone, each atom of elemental hydrogen has one electron orbiting its nucleus in a 1s orbital. The phase of each 1s orbital in these two hydrogen atoms is identical, which is indicated on this slide with the plus symbol and the color yellow. The electron is indicated with the letter E superscript minus. Note that the plus symbol does not mean that the hydrogen atom is positively charged. Here we use this symbol only to designate that the phase of the 1s orbital is positive. To form a bond, the two atoms must approach one another. They are both attracted and repelled from each other by electrostatic forces. These forces include attractions between the electrons and the nuclei of each atom, repulsions between the two nuclei, and repulsions between the two electrons. If we examine a potential energy diagram of the system, we can see that as the two elemental hydrogen atoms approach one another, the energy of the system decreases or becomes more stable. In fact, this energy continues to decrease until it reaches a minimum, in this case, negative 436 kilojoules per mole for molecular hydrogen. Note, however, that if the nuclei continue to approach each other, the energy of the system dramatically increases with small decreases in the internuclear distance. This results from the mutual repulsion of the protons in each nucleus as well as the electrons in each atom. In effect, at an optimum internuclear distance, the system is stabilized because each nucleus is shielded from the other nucleus by the pair of electrons shared between them, and held in place in space by each nucleus's mutual attraction to those shared electrons. For molecular hydrogen, this optimum distance is approximately 74 picometers. We can visualize this on the next slide by merging the two atomic orbitals into a shared molecular orbital with the electron pair located between the two nuclei. Again, the nuclei are drawn together because of the attractive force between the protons in each nucleus and the electrons in each atom. We call any molecular orbitals that result from the combination of two s orbitals sigma bonds. These bonds include orbitals that overlap along the internuclear axis. If we visualize the formation of molecular hydrogen using electrostatic potential maps, we can see that the individual 1s orbitals merge together as they approach into the sigma bond. Here on this slide, the white bar represents the internuclear axis between the two hydrogen atoms. Notice that as the two atoms approach, the color key indicates that the electrons are located primarily in the red region between the two nuclei, which minimizes the potential energy of the system by shielding the nuclei from one another with the shared electrons. Molecular orbital theory offers a more precise model that describes the behavior of electrons in covalent bonds by using wave equations to calculate the precise shape and energy of electrons in molecules. Following the Pauli exclusion principle, molecular orbitals contain no more than two electrons, just like atomic orbitals do, and molecular orbitals are expressed using a combination of atomic orbital wave functions. Importantly, MO theory demonstrates that for every AO combined, an equivalent number of MOs, molecular orbitals, are produced. Thus, combining two AOs will produce two MOs. Combining four AOs will produce four MOs, and so on. The resultant molecular orbitals include a bonding combination indicated with the Greek letter psi, and an antibonding orbital indicated with the Greek letter psi star, you can see down at the bottom of the slide. Bonding combinations are lower in energy and correspond to constructive wave interference between two atomic orbitals. Antibonding combinations are higher in energy and correspond to destructive wave interference between the two atomic orbitals. Let's take a look at the relative energy of molecular orbitals that result from the combination of two atomic orbitals. Again, we will first focus on a simple molecule of hydrogen to exemplify the point. Here on this slide, you can see that each hydrogen atom is indicated with one electron in a 1s orbital. In the energy level diagram in the middle, we place two 1s atomic orbitals at equivalent vertical distances from the base of the slide to illustrate that they are equal in energy because they both represent a single hydrogen atom. Using blue arrows, we indicate the single electron contained within the 1s orbital of each hydrogen atom. When the two atomic orbitals mix together, they can do so either constructively to produce a bonding orbital or destructively to produce an antibonding orbital. The bonding molecular orbital is lower in energy as the overall system is stabilized by the sharing of electrons by both nuclei. The antibonding orbital up top is much higher in energy as the electrons are here localized on each nucleus. The lack of electron shielding between each nucleus dramatically increases the energy of the systems as the protons are free to repel one another. As before with valence bond theory, we label the bonding orbital that forms from the combination of any two s orbitals as a sigma bond. What is more now with molecular orbital theory, we can label the antibonding orbital a sigma star molecular orbital, indicated at the top of the slide. The increased precision of molecular orbital theory allows us to explain the observed shapes of organic molecules as well as their mechanism of formation. Here we can see a simple molecule of methane, CH4. We have observed before that the geometry of methane is tetrahedral, that it has equivalent degenerate CH bonds of bond angle 109.5 and bond distances of 110 picometers. The structure, however, that we've observed in the laboratory of methane is inconsistent with the electron configuration of neutral carbon, which we would use according to valence bond theory to explain the formation of molecular orbitals. Looking at the electron configuration of neutral carbon, we can see that valence bond theory cannot predict the observed empirical data of the bond angles or bond distances in methane. Recall that valence bond theory states that covalent bonds must form from the simple overlap of half-filled atomic orbitals. Looking at the electron configuration of neutral carbon, we see that the valence shell contains only two half-filled p orbitals. As such, valence bond theory predicts that carbon can only bond with two hydrogen atoms to form CH bonds that must be at 90 degrees to one another. We already know, however, that the empirical data from the lab shows us that this is not the observed geometry or number of bonds in a molecule of methane. In contrast, molecular orbital theory readily explains this by demonstrating that the individual atomic orbitals in carbon can combine to form hybrid orbitals with new shapes and energies that participate in covalent bonding. Molecular orbital theory explains this through the promotion of one electron from the 2s orbital to an empty p orbital. These four orbitals can now hybridize or mix together to become four new orbitals of degenerate energy. And each of our four electrons from the original atomic orbitals can now occupy one of the new four hybrid orbitals. Here we now have four equivalent half-filled orbitals that can each form one CH bond in a manner that's consistent with the observed number of bonds in methane. Because we formed these hybrid orbitals from one 2s orbital and three 2p orbitals, we refer to each of the hybrid orbitals as an sp3 orbital. So as you can see here on this slide, one 2s orbital plus three 2p orbitals equals four sp3 orbitals. Remember, each hybrid orbital in this case is labeled as an sp3 orbital. A lot of students confuse the superscripted numbers used to label hybrid orbitals with the exponents that they've seen in general chemistry used to indicate the number of electrons in electron configuration notation. Note that electron configuration uses this number to indicate the number of electrons that exist in each orbital in a neutral atom. Hybrid molecular orbital theory, though, used these numbers to indicate the number of each type of atomic orbital that was combined to produce the hybrid molecular orbital. The shape and geometry of methane is predicted by molecular orbital theory if we look at the individual shapes of each hybrid sp3 orbital. Remember, combining the 2s orbital with each of the three p orbitals produces four equivalent sp3 hybrid orbitals that have a large lobe of one phase indicated in red and a smaller lobe of opposite phase indicated in blue. These same colors can be found in the p orbitals where each lobe is of similar size but opposite phase. The 2s orbital down here indicated in red is in the same phase as only one lobe of each of the p atomic orbitals. It is in the opposite phase of the other lobe of each p atomic orbital indicated in blue. Constructive interference between the two atomic orbitals produce a large red lobe in the sp3 hybrid orbital, while destructive interference produces a smaller blue lobe in each of the hybrids. It goes without saying that orbitals are not red or blue. Orbitals do not have plus or minus signs in them, and we only use color and these symbols to help us visualize the relative location, shape, and sizes of our hybrid orbitals. Returning to our simple 2D drawings, we can see that each of the four hydrogen atoms can overlap with one of the new sp3 hybrid orbitals of carbon to produce four equivalent CH sigma bonds in methane. Remember that although I have not shown it here, the combination of the 1s orbital in hydrogen and any one of the 2 sp3 orbitals in carbon also produces a sigma star antibonding orbital. Recall that for every atomic orbital that combines, you get one bonding molecular orbital and one antibonding molecular orbital. For a truly amazing educational video regarding molecular orbital theory, I encourage students to watch the 30-minute clips from Spahn-Holtz production to enrich their understandings. Here on this slide, I provided you the credentials to access the public stream for our course, but some students may wish to purchase the video on their own so they can watch it at their convenience at any location of their choosing. That is it for today's pre-lecture. As always, make sure you review the relevant readings and come to class prepared to apply what you have learned.